Hello student, to the course of Physics of Linear and Nonlinear Optical Waveguides. So, today we have lecture 43 and we started some calculation regarding fiber backgrating. Today we are going to continue with that calculation, which is eventually the reflectivity calculation. So, let me write down so far whatever the expression we got. So, our aim here is to, this was the backgrating structure and I had a wave psi forward and then psi backward. My big psi was psi forward plus psi backward, and this psi forward is associated with the amplitude term Az, and this backward is associated with another amplitude term B. We wanted to find out this wave equation for fiber backgrating. And psi was in total a function of z e to the power of I beta 1 z plus b e to the power of minus of I beta 1 z psi 1, which is a function of x, and then e to the power of minus I omega t. That was the by definition that was the psi. Then I try to execute this term, which is sitting in the left hand side. This is equivalent to of psi, and we derive equation 1 as this was we derive as beta 1 square minus k 0 square in 1 square big psi. That was one equation we derived, and the second equation that we derived is this. Dz e to the power of I beta 1 z minus del b del z e to the power of minus I beta 2 z, then psi 1 e to the power of minus I omega t, and then minus of beta 1 square big psi. That was the two equation we derived last time. So, now we execute the left hand side, because two terms, the partial derivative of x and partial derivative with respect to z, these are now evaluated. So, we will just put it. So, the left hand side which is equivalent to this is simply 2 I beta 1, just add these two terms, then del A del Z e to the power of I beta 1 z minus del b del z e to the power of minus I beta 2 z, then psi 1 e to the power of minus I omega t, and then this term plus beta 1 square rather big psi minus k 0 square n 1 square big psi, and another beta 1 is here. So, I missed that. So, minus of beta 1 square psi I should write here only. So, these two terms will going to cancel out, beta 1 square plus and beta 1 square, these two terms will going to cancel out. So, this is roughly the left hand side 2 y beta 1 del a del z e to the power of I beta 1 z minus del b del z e to the power of minus I beta 2 z and rest of the term. So, this is the left hand side. Now, let us concentrate what in the right hand side. So, right hand side. So, in the right hand side we have n square divided by c square del 2 psi del t square, that was the term. Now, in the psi, if I look what is my psi here, these t dependency is here with minus I omega t. So, only minus omega square term will come out, and then we have n square, then I have c square and simply big psi. Now, omega divided by c square I can write it as minus of k 0 square and n square psi. Now, we should remember what was the n square we derived for bracketing. So, let me write it once again. N square was n 1 square plus sigma sine of k z, that was the n square we derived earlier. So, this quantity is simply n square divided by c square d2 psi dt square. This quantity is simply minus of k 0 square and then n 1 square plus sigma sine k z bracket close, and then I have big psi. So, here you should remember the sigma was 2 n 1 delta n. So, this is the roughly the right hand side. So, I execute the left hand side of the equation and then right hand side of the equation. So, these two things should be equal, because according to the wave equation xi square. So, this is the wave equation we had. So, now I equate this left hand side and right hand side. Left hand side I know and right hand side also I know right now. So, I can write as the wave equation from the wave equation we have 2 I beta 1 So, whatever the term I have here, I should write it. So, 2 I beta 1, then del A del Z e to the power of I beta 1 Z minus del B del Z e to the power of minus I beta 1 Z, then psi 1 e to the power of minus of I omega t, then minus of k 0 square n 1 square big psi. That is in the left hand side. I just write this one. The right hand side, that should be equal to, this should be equal to this one, whatever we derived here. So, minus of k 0 square n 1 square plus sigma sine k z bracket, better to put a third bracket, and then big psi. Kindly note that this k 0 n 1 square psi and this k 0 n 1 square psi will go to cancel out. So, this term and this term will go to cancel out. So, eventually we have eventually we have 2 I beta 1 and then del A del Z e to the power of I beta 1 Z minus del B del Z e to the power of minus I beta 1 Z, then psi 1 e to the power of minus I omega t as usual, and then in the right hand side I can have minus of k 0 square, then sigma, then sine of k z, and I have a big psi. So, I just write down the big psi once again with its form. So, it should be A e to the power of I beta 1 z plus B e to the power of minus I beta 1 z bracket close psi 1 and e to the power of minus of I omega t. Now, again this quantity psi 1 and psi 1 will going to cancel out here, and e to the power I omega t and e to the power I omega t also going to cancel out. So, these two terms will going to cancel out, and I can write this expression as by dividing. Now, what I do, I divide 2 I beta 1 from left hand side and right hand side, and also I divide 2 e to the power I beta 1 z, so that I can have a free term like del A del z. So, if I do, I can have del A del z, I want to free this term, minus del B del z e to the power of minus of 2 I beta, because I divide everything with e to the power of I beta z. So, e to the power of minus 2 I beta 1 z plus, I put everything in the right hand side, plus k 0 square sigma sine kz divided by 2 I beta, because I divide this term as well, 2 I beta 1 was there. So, I divide this 2 I beta 1 again, and rest of the term, which is A, because I divide e to the power I beta 1 z here also. So, it should be A plus B e to the power of minus 2 I beta 1 z equal to 0. That is the total expression. Next thing is interesting. I write this sine kz, I can write as e to the power of I big kz minus e to the power of minus I big kz divided by 2 of I, and I will going to put it here, so that I can have an expression like dA d minus del B del Z e to the power of minus 2 I beta 1 Z minus k0 sigma divided by 4 beta 1, and this term I write as e to the power of I kz minus e to the power of minus I kz, this, and then A plus B e to the power of minus of 2 I beta 1 z equal to 0. This is the complete equation. Now, next I write del A del Z minus del B del Z e to the power of minus 2 I beta 1 Z minus k0 sigma divided by 4 beta 1, and I multiply these things there. So, I will going to have a term like A into e to the power of I k z minus e to the power of minus I k z plus B into e to the power of I k minus 2 I beta 1 z, that is one term I am having, and then I have minus this is I have beta e to the power a I plus, and then this term, second term, will be minus b e to the power of minus I, then b k plus 2 I beta 1 then z bracket close equal to 0. So, I am having many terms. Now, let us try to understand how many exponential terms are there. So, here we have first exponential term, here we have second exponential term, here we have third exponential term, this is having fourth exponential term, and finally, I have fifth exponential. So, there are 5 exponential terms. So, let me write down all these 5 exponential terms. So, first term is e to the power of minus 2 I beta 1 z, second term is e to the power of minus I k z, third term is e to the power of, sorry, this is plus, so minus I k z, fourth term is very important term, e to the power of I k minus 2, sorry, here since I take I common, I have a mistake here. So, this I should not be here. So, 2 beta 1 z, and finally, I have fifth term with e to the power of I with a negative sign kappa, sorry, k plus 2 beta 1 z. Now, you can see among these 5 terms, only this fourth term which I need to highlight, this term will vary slowly and other term will vary very rapidly. Why it is slowly varying? Because there is a condition that k can be equal to 2 beta 1. If this condition is valid, then we can have a Bragg condition. So, among all the 5 terms, so I can write it here, except the fourth term, other exponential term will vary rapidly. With increasing z, this term will vary very rapidly compared to this one, because I have k. So, there is a possibility that kappa is equal to 2 I beta. If that is the case, then this term can be 1. So, there will be no rapid variation of that term. So, neglecting those, rapidly varying terms, neglecting those rapidly varying terms, we can have, so you can see we can have a very simple expression, and that expression is delta A delta Z is nearly equal to k0 sigma divided by 4 beta 1, then B the phase term I b k minus 2 beta 1 z. So, I am having a simple expression which, after doing all these things, which tells me how dA dz is varying. That is the aim from the very beginning. Now, let kappa is equal to k0 sigma divided by 4 beta 1. I just rename all these things, and gamma is equal to this phase term b k minus 2 beta 1, just rename. Then I can have an expression like del A del Z is nearly equal to kappa b e to the power of I gamma z. So, this is the expression I am looking for. I am having the expression of the variation of the forward amplitude of the forward propagating wave. In a similar way, exactly in the similar way, In a similar way, similarly, we can have a term corresponding to B, and this will be like that, kappa B, sorry, here it will be A because it is coupled with A now, A e to the power of minus I gamma z. That is the another equation you can have. And how you get this equation? If you go back to this equation, the equation we had here, this is the equation I am talking about. In the next line, what I do, I just divide this equation with respect to e to the power I beta z and 2 I beta 1. I divide this entire equation both the side with 2 I beta 1 multiplied by e to the power I beta 1 z. I can also do the same thing, but I can divide 2 I beta 1 e to the power I beta 1 z minus I beta 1 z. If I do that, then instead of having del A del z free, I can have another term which is del B del z which is free. Then I can write this equation in a exactly similar way and do all the procedure that we have done here, and we can end up with this equation del B del z is nearly equal to kappa A e to the power I gamma z. So, whatever the aim in our in this calculation, that how to find out the evolution of A z and B z will happen when the wave is propagating inside this bracketing, we managed to find these two equations, that these are the two expressions which guide us that how the A and B will going to vary inside the fiber bracketing, and these are related to certain phase term, very important phase term, which is k minus 2 beta 1. So, today I do not have that much of time to expand more what is going on. So, in the next class we will start from these two equations and then study the reflectivity, we complete the calculation of the reflectivity, that because in the fiber bracketing what happened, I launch a light and a particular wavelength is reflected from these bracketing. So, this bracketing behaves like a mirror. So, since it is behaves like a mirror, I can calculate the reflectivity of this system, and that is the calculation precisely we are doing in this course, in this particular in this couple of classes. So, in the next class we will start from this equation and try to understand how A and B one can evaluate by solving these two coupled differential equation. So, with that note I would like to conclude. Thank you very much for your attention and see you in the next class.